Good afternoon. This is Mechanics of Materials. So we are working in chapter 7 of the statics textbook. Author is R.C. Hibbeler. That's the 5th edition. So in the previous lecture, we were working through our internal resultant loadings. And we solved problems that dealt with normal force, N, shear force, V, and our bending moment. Say about point O. And typically we said the point O is most often, we should say, set to be at the centroid of the body or the section area. And we can get our centroid locations from for different shapes from Appendix B. Using equations from Appendix B in the text. So we solved some problems using related to these internal resultant loadings. Then we talked about stress and strains. We talked about average, normal stress, where N is the internal resultant normal force, and A is the cross-sectional area. And we define stress as the intensity of the internal force acting on a specific area we'll say passing through a point. We talked about our average shear stress. V over A, where V is the internal resultant shear force, and A is the cross-sectional area or area of the section. And we talked about, we worked problems dealing with pins where it could be double shear or single shear. So let's work a couple more problems dealing with these concepts, and then we'll go into something new. So if we can, let's take a look at problem 7-5 in your text. This is on page 322. The problem states, determine the resultant internal loadings acting on the cross section at point B. So we have a cantilevered beam here with a distributed loading, triangular area. This is A, C, and point B is somewhere here. This distance here is 12 feet. This distance here is 3 feet. The problem wants us to determine the internal loadings acting at point B. So we can look at this too. So we're making the cut. We're making a section or cut at point B. So if we do this, we can be left with two segments to work, either segment AB or segment BC. If we work with AB, then we need to know the support reaction at A. But if we work segment BC, then we do not have to worry about a support reaction. So if we redraw our free body diagram after the cut for BC, let's go back. So we're making our cut right here. This is BC. This distance here is 12 feet. So since we made the cut, we have our normal force at B, our shear force, and our bending moment at point B. Those are internal resultant loadings that we have to solve for. Now, initially, the intensity of the distributed loading was 60 pound force per foot. So now with a different length, we have to figure out our new intensity. So initially it was 60 pound force per foot for the triangle of base length 15 feet. What is our new loading for the triangle of 12 feet? Cross multiply and divide. Your new intensity is 48 pound force per feet for the distributed loading. Now we need to represent this distributed loading as a resultant force. We know from our appendix B, it occurs 1/3 on the larger side of the triangle where the resultant force represents for a triangle, and it's equal to the area under the distributed loading curve. This is a triangle, so the area is given by 1/2 the base, 12 feet, times the height or the intensity of the loading, 48 pound force per foot. This is 288 pound force. Okay, so now we can begin working. Using our equations of equilibrium, sum of our forces in the x direction equal to 0. We have negative MB equal to 0. Therefore, MB equals 0. That's our normal force at B. Sum of our forces in the y direction, we have our VB, which is our shear force at B, minus our resultant force from the loading. These are the only two forces in the y direction. So one unknown left is our bending moment at B. So we'll take the sum of all our moments about point B. So we have to count our bending moment. Remember, clockwise rotation is negative. Counterclockwise is positive. That's our orientation. We have to take into account the 288 pound force from the resultant loading. And its perpendicular distance to point B is causing a clockwise, so negative. So it's minus the 288 the perpendicular distance to point B. This is 4 feet. Remember, it's 1/3 the length. 1/3 of 12 feet is 4 feet. So you get 1,152 pound force feet. So the negative sign indicates that the moment acts in the opposite direction as to how we have it on the free body diagram. Okay, so let's work some problems dealing with stress. Take a look at problem 7-30. This is page 342 in your text. The problem states, if the material fails when the average normal stress reaches 120 psi, Determine the largest centrally applied vertical force P the block can support. So this is something like a rectangle with some area missing on the two ends. So let's find the cross-sectional area of the block. Okay, if we do a simple length times width, the length, and if we treat it as a rectangle, the length is 12 inches plus 1 inches plus 1 inches, so that's 14 inches. The width is 4 inches plus 1 inches plus 1 inches, that's 6 inches. But we have two void spaces on both ends, and they're equivalent. So the void is 4 inches wide by 1 inch long, and there are two voids, one on each side. So the total cross-sectional area is equal to the 14 inches times the 6 inches minus the void spaces, which we said is 2 times the 4 inches times the 1 inch. So the area is equal to 76 inches squared. Therefore, the allowable normal stress is the normal force allowed over the area. Well, they gave us the allowable normal stress, or the max, allowable or max, when it fails, so that's maximum, so that's the most you can allow, as 120 psi. PSI is pound force per inches squared, pound force inches squared, PSI equals to the N allow over the area, which we saw for 76 inches squared. You cross multiply something for your N allow, which is the vertical load here, the question is asking for, is the 76 times the 120, which is 9,120 pound force. Let's take a look at another problem. Look at 735. This is page 343 in the text. Okay. Here, the problem states, determine the average normal stress in each of the 20 millimeter diameter bars of this truss. So they said P is 40 kilonewtons. The diameter of every bar in the figure is 0.02 meters, 20 millimeters. So with normal stress, what we need to know is the normal force in each bar. Or each member of the truss. So if we go back to using our chapter 5 concepts, well, our method of joints, we can find the force developed in each member of the truss. And remember, we always start with at most 2 unknowns and at least 1 known at every joint. Start with a joint with at most 2 unknowns and at least 1 known value. So if we start with joint C, they gave us P is 40 kilonewtons. You have your FBC, which has to be to the negative x direction to balance out the 40 kilonewton force. Remember, every joint is in equilibrium. Therefore, our FAC has to be coming down to balance out the vertical component of the FBC. This is our orientation of the forces in the members. So that's our x direction, our y direction. 2 unknowns, FAC, FBC, 1 known. Now this truss is 1.5 meters vertical, 2 meters horizontal. So if you double that, that becomes a 3, 4, 5 triangle, which means this angle here, 3, 4, 5. The height of the truss is 1.5 meters. 2 times 1.5 is 3. The bottom length is 2 meters. 2 times 2 is 4. So the hypotenuse of this triangular truss must be 5. The ratio would be 3, 4, 5 for this triangle. It's a ratio. So then using our equations of equilibrium for this joint, sum of our forces in the x direction equals 0. We have your 40 kilonewtons minus your FBC. We want the x component, so that's 4/5. That's the ratio, equals 0. And your FBC is 50 kilonewtons. Sum of your forces in the y direction equals 0. You now know what FBC is. So that's the 50 kilonewtons FBC times the 3/5 to get the vertical component of the FBC minus your FAC. Therefore, your FAC is 30 kilonewtons. AC is in tension. FBC is in compression. FBC is pushing at the joint, and FAC is pulling from the joint C. Then, if we work joint B, it's on a roller, so the support reaction there is just a vertical. So you have your BY. To balance that vertical component there, your FBC must be coming down. We determine FBC to be 50 kilonewtons. And this angle, once again, is 3, 4, 5 triangle. That's the ratio. And you have your FAB. The x component has to balance out the FBC, so it goes in the negative x direction. So once again, we have two unknowns and one known. So using our equations of equilibrium, sum of our forces x direction equals 0. We have your FBC, positive x direction. We want the x component, that's the 4/5, minus your FAB equals 0. Solve that out. FAB is equal to 40 kilonewtons and is pulling from the joint B, so it's in tension. Now the question asked us, what is the average normal stress in each of the 20 millimeter bars? So the area of each bar of the truss is pi r squared, or pi over 4 d squared. And d was given as 0.02 meters. So the area of the bar is 3.14 times 10 to the minus 4 meters squared. So my average normal stress, go to a clean page. Is the force in the bar divided by the area. So we have 3 bars here. We have AC, AB, and BC. So as a recap, we had our FBC, we determined was 50 kilonewtons. Our FAC was 30 kilonewtons. And our FAB was 40 kilonewtons. So our average normal stress in the bar BC will be our FBC over the area. So it's 50 times 10 to the 3. Kilo means 10 to the 3 newtons over the 3.14 times 10 to the minus 4 meters squared. This gives you, remember, 1 Newton over meter squared is 1 Pascal. So mega being 10 to the 6, this is 159 megapascals. The average normal stress in bar AC is 30 times 10 to the 3 newtons. This gives you 95.5 megapascals. Lastly, the average normal stress in bar AB this comes out to be 127 megapascals. work out a problem dealing with average shear stress. Let's look at problem 738, page 343 in text. Problem states set P to 5 kilonewtons. Then determine the average shear stress in the pins at A, B, and C. All pins are in double shear. And each has a diameter of 18 millimeters, 0.018 meters. So it's a pin. They want to know the shear stress in the pins A, B, and C. So let's draw a free body diagram. So we can replace the BC, is the force there is FBC. This is a 3-4 3-4-5 triangle there. P is 5 kilonewtons, so you have 5 kilonewton here. You have 3 times 3P, so it's 15 kilonewtons here. You have 6P, 6 times 5, 30 kilonewtons here. And you have another P, so 5 kilonewtons here. Then for your A, you have your AX, have to balance out the FBC, and your AY. So first, to do our support reactions, we take out some of our moments about point A. We can then do not have to worry about solving for AY and AX. We can solve for FBC. So we'll consider all the forces that create a tendency to rotate about point A. Clockwise being negative clockwise rotation being negative, counterclockwise rotation being positive. So at about point A, all the loadings of P cause counterclockwise positive rotation about point A. The FBC vertical component causes clockwise, so negative. The perpendicular distances here, this is 0.5 meters. This distance here is 1.5 meters. This is 2 meters. This is 1.5 meters. And this is 0.5 meters. So about point A, we have the 5 kilonewtons times the perpendicular distance of 0.5 meters, plus the 30 kilonewton times the perpendicular distance of 2 meters, plus the 15 kilonewton force times the perpendicular distance of 4 meters, plus the 5 kilonewton force times the perpendicular distance of 5.5 meters, minus the FBC. We want the vertical component so we can get a perpendicular distance. So that's the 3/5 ratio times the perpendicular distance of 6 meters. Solve for FBC. You get 41.7 kilonewtons. take the sum of our forces in the x direction equals 0. You have your FBC, so your 41.7 kilonewtons, times the horizontal component, which is the 4/5, minus your AX. Therefore, your AX is equal to 33.3 kilonewtons. Take out some of our forces in the y direction. You have your AY, which is your last unknown, minus 5 kilonewtons, minus 30 kilonewtons, minus 15 kilonewtons, minus 5 kilonewtons, plus your FBC, which is the 41.7 kilonewtons, times the vertical component 3/5 equals 0. Your AY is 30 kilonewtons. So now, as a recap, we know FBC was 41.7 kilonewtons. Our AX is 33.3 kilonewtons, and our AY is 30 kilonewtons. All pins are in double shear, which is given in a problem statement. So since everything is in double shear for shear stress, we need to know the shear force, V. So for the pins at B and C, VB is equal to VC. Double shear, this is the pin, you have your FBC, and you have your, which we said was 41.7 kilonewtons, and you have your VB or your VC coming down. Double shear. Therefore, VB we said equals to VC is your FBC over 2. For equilibrium, double shear is equal to the force in FBC over 2. 2V equals FBC. So this is 41.7 kilonewtons over 2. So then for VA, we need to know FA. And FA, for our chapter 2 concepts, is AX squared plus AY, the square root of AX squared plus AY squared. So it's the square root of 33.3 kilonewtons squared plus 30 kilonewtons squared. FA, 44.9 kilonewtons. Therefore, our VA, once again double shear, is FA over 2. So VA is 22.42 kilonewtons. The diameter of the pins is given as 18 millimeters, is 0.018 meters. So the area is pi over 4 d squared. Two 2.54 10 to the minus 4 meters squared is the area of the pins. So the average shear stress at B and C are equal. We said then it's the VB/C over the area. We said our VB or VC is 20.83 kilonewtons. So it's 20.83 times 10. Kilo means 10 to the 3 newtons over our 2.54 times 10 to the minus 4 meters squared. Remember, 1 Newton per meter squared. 1 Newton is 1 Pascal. So this units of newtons per meter squared. Divide that out. You get 81.9 megapascals. So the shear stress in pin at A, VA over A, 22.42 kilonewtons, so that's 10 to the 3 newtons. This is 88.1 megapascals. Look at another problem. Problem 7-41 in the text. It's page 344. This problem states, the beam is supported by 2 rods, AB and CD, that have cross-sectional areas. So rod AB area equals to 12 millimeters squared. And you have rod CD area equals to 8 millimeters squared. If the D, the distance, equals to 1 meter, determine the average normal stress in each rod. So drawing our free body diagram. So this is our force in rod CD. This is our force in rod AB. And we have our 6 kilonewton force coming down here. This is 1 meter. And the entire length is 3 meters. So we need to know the force in the rods AB and CD. So take the sum of the moments about point A equals 0 for equilibrium. We have your FCD times 3 meters minus 6 kilonewton force times the 1 meter. FCD is 2 kilonewtons. Take the sum of my forces in the y direction equals 0. You have your FAB minus your 6 kilonewtons plus your 2 kilonewtons equals 0 for equilibrium. FAB is 4 kilonewtons. Therefore, the average normal stress in rod AB is FAB over the area AB. So it'll be 4 times 10 to the 3, 4 kilonewtons over the area of AB. They gave the area 12 millimeters squared. Well, we need it in meters squared. So 1 meter squared, if 1 meter is equal to 1,000 millimeters, so then 1 meter squared is 1,000 times 1,000. Which is 10 to the 6 millimeters squared. So the normal stress here in rod AB comes out to newtons per meter squared, 333 megapascals. For rod CD, FCD over the area in rod CD. FCD we said was 2 kilonewtons, so that's 2 times 10 to the 3, 2 kilonewtons. The area given in this rod was 8 millimeters squared. What we need in meters squared times 1 meter squared is 10 to the 6 millimeters squared. The average normal stress in rod CD is 250 megapascals. 1 newton per meter squared is 1 pascal. So let's move on to section 7.6 in the text. Allowable stress design. So to ensure the safety of a structure or mechanical member, it is necessary to restrict the applied load to one that is less than the load the member can fully support. I want to restrict the applied load to less than the load the member can fully support. And there are many reasons for doing this. You give unknown vibrations that can occur but may not be accounted for in the design. Atmospheric corrosion, which causes the material to deteriorate. And there are other possibilities. So one method of specifying the allowable load is to use a number called factor of safety is a ratio of the failure load to the allowable load. Factor of safety is the failure load, allowable load. This can be set as the allowable, the normal stress that would fail over the allowable normal stress. Likewise with the shear stress. So let's work out a few problems that take this concept into mind. Let's look at problem 758 in your text. This is on page 358. Okay, so this problem states, determine the size of the square bearing plates, A prime and B prime, required to support the loading. P is 1.5 kilopounds, 1,000 pounds, KIP, this is kilopounds. Dimension, take P equal 1.5 kilopounds. And they want us to size the plates to the nearest ½ inch. The reaction at the supports are vertical only, and allowable bearing stress for the plates equals 400 psi. Bearing stress, let's define that right quick, is the compressive stress caused by one surface that bears against another. So they gave us the allowable stress. So drawing our free body diagram, P is 1.5 kip. You have 2.5 kip coming down here. You have 3 kip coming here, 2 kip coming here, and 2 kip coming here. This distance here is 5 feet, 5 feet, 5 feet, and 7.5 feet. You have your AY, your support there, vertical, and say your BY, your support here. So we solve for these support reactions. It would take out some of our moments about point A. It'd be our BY times the perpendicular distance here, 15 feet, minus your 2 kip times 5 feet, counterclockwise rotation being positive, clockwise rotation being negative, minus your 3 kip times 10 feet, minus your 2 kip, So minus your 2 kip times 15 feet, minus your P, which is really 1.5 kip, times 22.5 feet, equals 0. Solve this out. Your BY is 6.91 kip. If there was sum of forces in the Y direction, equals 0. Equation of equilibrium. You have your AY plus your BY, 6.91 kip, minus your 2 kip, minus your 2 kip, minus your 3 kip, minus your 2 kip, minus your 1.5 kip, equals 0. So your AY is equal to 3.59 kip. So it's AY 3.59 kip. And your BY was 6.91 kip. So then, to find the bearing stress in each of the plates, for plate A, the allowable, which was given to us as 400 psi, 400 pound force per inch squared, psi, pound per inch squared, is equal to our force in the plate, our AY, which is 3.59 kip, which is 10 to the 3 pound force, over our area of plate A. So the area of plate A, cross multiply and divide, you get 8.975 inches squared. Well, these plates are square plates. So for the dimensions, take the square root of this. And you get 2.99 inches. So to the question said to the nearest half inch. So plate A will be a 3-inch by 3-inch plate to support that load. For plate B, once again, the allowable is 400 psi, pound force per inch squared. Our BY was 6.91 kip, which is 10 to the 3 pound force. Allowable stress is force over area. So area of plate B, cross multiply and divide. (17.275 inches squared). Once again, this is a square plate. So the dimensions equal to square root of 17.275 inches squared. Which is 4.16 inches. So the dimensions to the nearest half inch will be a 4 1/4 plate, so 4.25 inches by 4.25 inches. To another problem. 7-60. Here it says determine the required diameter of the pins at A and B. This is page 358 in your text. Turn the required diameter pins at A and B to the nearest 1/16 inch if the allowable shear stress from the material (6 KSI, kilopounds per square inch). Pin A is double shear. Pin B, single shear. So drawing our free body diagram. A is a pin, you have a AX, AY, 3 kip that way. D is a rocker, so you have your DY. This is 12 feet. That's 6 feet and 6 feet. 8 feet of height. 6, 8. So if you divide by 2, it'll be 3, 4. This is a 3, 4, 5 triangle ratio. So for my support reactions, I'm going to take some of my moments about point D equals 0 for equilibrium. AX lines of action goes to point D, so there's no perpendicular distance. AY causes a counterclockwise positive rotation. AY, perpendicular distance to D, is 12 feet. Minus the 3 kip horizontal force at the top, which is causing clockwise rotation about point D. So it's minus. Perpendicular distance there is 8 feet. AY is 2 kip. 24 divided by 12 is 2. Then sum our forces in the X direction. You have your 3 kip minus your AX equals 0. Therefore, your AX is equal to 3 kip. So then my FA, the force in the pin at A, square root of AX squared plus AY squared, square root of 3 kip squared plus 2 kip squared, 3.61 kip. So now to get the force in pin B, we need to consider if we look at joint C, joint C has the 3 kip force. You have FCD. And you have FBC. As we said previously, this is a 3, 4, 5 triangle. So for this joint, if we consider our sum of our forces in the x direction equals 0, you have your 3 kip minus your FBC times a horizontal component, which is 3/5, equals 0. FBC five kip. So the problem told you that pin at A is double shear. This is the pin at A. You have your FA, which we calculated to be 3.61 kip. You have your VA. So FA is 2 VA. So VA is FA over 2. 3.61 kip over 2. This is 1.805 kip. So then my allowable shear stress at A was given as 6 KSI, and they want a diameter. So let's set our equation up. This is VA over the area. Six KSI is 6,000 pounds per inches squared equals VA, which is 1805. Kip is kilopounds, so it's 1,805 kilopounds over the area. Cross multiply and solve. Area is 0.3 inches squared. Since they gave you the diameter, you know area for a circle is pi over 4 d squared. So pi over 4 d squared is 0.3 inches squared. So D is equal to 0.619 inches. They want the nearest 16th inch. So you can round it up to, for pin A, the diameter of the pin A is 5/8 inches. For pin B, which is single shear, so this is the pin, you have your FBC, which we calculated as 5 kip, and you have single shear VB, so VB is equal to FBC. Once again, our allowable shear stress was given as 6 KSI, so it's 6,000 pounds per inches squared, which is equal to our VB, which is 5,000 pounds force, 5 kilopounds, 5,000 pounds, over our area, we'll say sub B. Area B (0.833 inches squared) pi over 4d, say b squared, is equal to 0.833 inches squared. Your diameter is equal to 1.03 inches. To the nearest 16th, round up to 1.116 inch. So let's talk about deformation. So whenever a force is applied to a body, it will tend to change the body's shape and size. These changes are called deformation. They can be highly visible or practically unnoticeable. Practically unnoticeable. So here we introduce the concept of strain. Strain is determined by experiment. So normal strain we are concerned with changes in lengths. So if an axial load is applied to, say, a bar, we have a load P, So the initial length L sub O is the initial length before the load is applied. And once the load is applied, the new length is just L. L sub O is initial length. L, we'll say, is final length. So then the average normal strain, this is epsilon, so the average normal strain, epsilon, is the final length over the minus the initial length over the initial length. Delta is the final minus initial. So this could be written as the change in the lengths over the initial length. So epsilon is a change in the length per unit length. So it is a unitless quantity. However, it's sometimes noted as a micrometers per meter. So it's normal strain. Shear strain concerns deformations that cause line segments to change direction. If two line segments that are originally perpendicular to one another, then after the force is applied, the change, remember perpendicular means it's a 90-degree angle between them, then the change in the angle that occurs between them is referred to as shear strain. And this angle is gamma. And it's measured in radians. And it's our conversion between degrees and radians. Remember pi radians equals 1 to 80 degrees. So 2 pi radians equal 360 degrees. Pi over 2 radians is 90 degrees. A quick review. So if we have two line segments and they're perpendicular initially, so the angle between them is pi over 2 radians, 90 degrees. And then you have a shear force V this way, so that your new deformed body has a new angle now, theta. Then if you initially were at a perpendicular 90-degree angle and your new angle is theta, then the change in the angle, we said, was gamma, which is our shear strain, the change in the angle that occurs between them. Gamma equals change in the angle between the line segments. So we started at a right triangle, perpendicular. A shear force was applied. So your new angle went from 90 degrees, or pi over 2 radians, to theta. The change is gamma. Therefore, gamma is equal to your initial pi over 2 minus the theta in radians. If the apply a shear force to the initial setting in this direction, once again, this change is gamma, but the new angle is theta. So the gamma, once again, but in this case, it's negative. So if your theta is greater than pi over 2, then the shear strain is negative. Take a look at some problems. Take a look at problem 771. This is page 370 in text. It says an air-filled rubber ball we got a rubber ball. Diameter is 6 inches. If the air pressure within the ball is increased into the diameter, new diameter is 7 inches. Determine the average normal strain in the rubber. So here, we're not talking about diameter. We're talking about if you were to take that ball and then change and then say make a cut here and elongate it into a line segment, that would be the circumference. So the strain is related to the circumference in this example, not the diameter. And we know circumference formula is pi times d, pi times diameter. So then our average normal strain, final minus initial over initial. So the final will be pi times d minus your initial, pi times do, over your pi times do initial. In this case, the pi's cross out. Maybe d minus do over do. Sub o means initial. So 7 minus 6. 7 inches minus 6 inches over 6 inches. 0.167 inch per inch. That's the average normal strain in the rubber. Take a look at another problem. It's page 370 in your text. It says a thin strip of rubber, unstretched length, so it's your L sub O, 15 inches. If it is stretched around a pipe having an outer diameter of 5 inches, determine the average normal strain in the strip. So the outer diameter is 5 inches, then the circumference is pi d. And that will be our final length. So your average normal strain is L minus L sub O over L. So it's 15.7 inches minus 15 inches. 15 inches. Average normal strain is 0.0472 inch per inch. Take a look at problem 778. This is page 371 in your text. Here it says the wire AB is unstretched when theta 45 degrees. If a load is applied to the bar AC, which causes theta to become load applied, theta becomes 47 degrees. Determine the normal strain in the wire. Okay, so let's draw a free body diagram. This length here is L. The bar length is L. The wire here, given this angle, this is theta. This is 47 degrees now, so this is 43. So then we have a new length then, we'll call it L prime or L. So the load is applied, which caused the wire to stretch, which changed the angle. So now it wants to know the normal strain in the wire with the load applied. So with a new length, once the theta became 47 degrees. So if we look at our cosine law, which we talked about in chapter 2, C equals to square root of A squared plus B squared minus 2AB times cosine of the angle C. So in that case, L equals to the square root of L squared plus L prime AB. L prime A sub AB is the new stretch length in the wire AB squared minus 2 times L times L prime AB times cosine of that angle 43 degrees. If I square both sides, that then becomes L squared is equal to L squared plus L prime AB squared minus 2L times L prime AB cosine 43 degrees. Let's go to a fresh page and rewrite that step. We squared both sides, that's L squared plus L prime AB squared minus 2L L prime AB cosine 43 degrees. So if you subtract L squared on both sides, these cross out, leaving you 2L L prime sub AB cosine of 40 degrees equals to L prime AB squared if I divide by L prime AB, this gives me L prime AB equals to 2L cosine 40 degrees. Therefore, my normal strain in the wire AB would be my final, which is my difference in the length, so my final length, which is the L prime AB, minus what it was before the load applied, just simply LAB over the initial LAB. Is I substitute the previous equations, I insert this into here, and I define, since initially it was a square, we know for a square, if every side is the same, the diagonal is a times the square root of 2. So in this case, we had LL, so this had to be LAB. So LAB is L times the square root of 2. Substituting both of those into my normal strain equation. L prime AB is 2L times cosine 40 degrees. That's substitution. minus LAB, which is L times the square root of 2, over LAB, which is L times the square root of 2. Rewrite that on a clean page. Normal strain wire EAB, 2L cosine 40 degrees minus L times square root of 2 over L times square root of 2. Solve that out. So it'll be L times 2 cosine of 40 degrees minus square root of 2 over L times square root of 2. The L's cross out. 2 cosine 43 degrees minus square root of 2 over square root of 2. Using your calculator, that comes out to be 0.0343. And that's the normal strain. We'll stop here today. If there's any questions, do not hesitate to send me an email. And good luck.